Hi to everyone, because I don't know if it is good morning, good evening, good afternoon, because we are all around the world. I will talk today about the theory we have recently developed for the calculation of complete and incomplete fusion of Willy bound systems. I start with a small review, very fast. The most simple situation we can have when we have tightly bound nuclei is the collision between some projectile and target to form a complete fusion compound nucleus formation. And then as it gets excited, we immediately have a decay of this complete nucleus. A simplest theoretical estimation of this process is we perform a potential scattering. Of course, in this case, we can have a short range imaginary potential, because if we have long range imaginary potential, what we get in this case is the reaction cross sections. If we have a short range imaginary potential, we can determine the transmission coefficients in this way, and then we can the fusion cross section in partial way the composition by this formula. An alternative version is to use a continuity equation, and through this imaginary potential, we get the fusion cross section and expectation value of the elastic wave function through this imaginary potential. But the life is not so simple like this. We know that we almost always have coupling to some reaction channels. So in this case, we have to perform couple channel calculations, or maybe we can first imagine that we can introduce two potentials, one that is a short range internal that correspond to the absorption to fusion, and surface potential that takes into account the absorption due to direct reaction channels. If someone tried to do that and try to calculate the fusion cross section, including only this short range potential, we immediately realize that the fusion cross section obtaining in this way will be extremely small. So this is not an alternative to calculate the fusion cross section. The reason is that as we have a surface imaginary potential, it will absorb almost all the flux, and almost no flux will arrive in this internal part of the barrier. This is if we take a short range imaginary potential. Of course, there was this is a so-called usually a Sachler school, but there is another school also you can find. I even have published some papers in the past in collaboration with Arturo Gomez Camacho from Mexico, that was a PhD of Udagawa, that was another school. In that case, they used an imaginary potential that also reached the surface, and a surface potential that is farther than this. In this case, you will have the part that goes to these inelastic channels that then come back to or goes to the part of flux that started from these inelastic channels that go to the flux that is what is taken into account when one performs coupled channel calculations. This is the case I'm showing here when we have some excited states. I'm putting here some picture, just not realistic picture. We solve this coupled equation, and from this coupled equation, we can take the absorption from each channel. In this case, by determination of the S matrix, we can determine the reaction cross sections. And from the reaction cross section, if we subtract all the direct reaction channel cross section, we get the fusion cross section. This is what usually do when we have a tightly bound system. But when we have weakly bound system, we know that we have all the components, all the reactions that can be active, besides the inelastic and transfer channels that are usually for the tightly bound, at least at low energy, because there is some words also that people are calculating in complete fusion in tightly bound system at high energy. I'm talking at energies around the Coulomb barrier only. Let's suppose that we have a projectile that can break into fragments. We can have different processes in this case. If the projectile is absorbed completely by the target, this is called the complete fusion. But if it breaks and both fragments are captured by the target, we can have also the complete fusion that cannot be distinguished from the experimental point of view. In this case, we have what usually people call sequential complete fusion. But we can have a situation where one or the other fragments are absorbed but the other not. In this case, we have the incomplete fusion of the first fragment or incomplete fusion of the second fragment. The sum of these incomplete fusions to the complete fusion, we get the total fusion. Of course, we can also have other channels like a non-capture breaker that you don't absorb none of these. Also, at the same time, we have elastic scattering, transfer reactions, or deep inelastic, or fission, or breakup triggered by transfers, a lot of channels. So, whoops. So I will do a small parenthesis here to describe a method we have developed in the past to study the effect of breakup channels on fusion cross sections to determine if the breakup enhance or suppress the fusion. We can use two main methods. One of them is to compare data with theoretical predictions, and the other one that is the most popular is the comparison of data for systems involving weakly and tightly bound systems. When we compare experiment versus theory, we can determine this delta sigma fusion, that is the difference between the experimental data and theoretical data. And this difference depends on the ingredients that were missing in the theory used to calculate the theoretical cross section. For instance, if we perform one channel or potential scattering with a potential that use standard densities, in this case, the difference between the theoretical and experimental part will arrive from dynamic and static effect altogether. If we perform a single channel, but if we use realistic densities, meaning in the case of double folding potentials, then the difference between these two quantities will arrive only from dynamics channels. If then we perform Cooper channel calculation, I mean usual Cooper channel calculation, if we put all the relevant bound channels, then the difference will arise only from the continuum couplings. And if we perform CDCC calculation and we are able to calculate all the ingredients, all the fusion cross section, then we should describe completely the fusion cross section and not have any difference between the experimental data and theory. So this is a method. I'm not talking now about the comparison, but this is what we propose in this talk. I will talk about the CDCC calculation to derive complete fusion and incomplete fusion. But coming back to the method to derive the effect of breakup on the fusion cross section, we can also compare fusion cross section of similar tightly and weakly bound systems. There is a gross difference between these systems. They may have different size due to they have different masses. They can have different Coulomb barriers. They can have different charges. And this we call usually trivial difference. So we have to take away all this difference. And for that, we have to perform a reduction of these data. As I said, recently we have proposed a universal fusion function method that consists of this transformation of the center of mass energy to these by these transformations, where VBA is the barrier, this is the curvature of the barrier, and inspired in the Won's formula. If we perform this kind of transformation to the Won formula, we obtain this system-independent function that we call universal fusion function. I would like to emphasize that sometimes people they say, no, but this method is inspired in the Won's formula that is not always valid. Okay, I agree, one formula is not always valid, but you can do that comparing only theory experiment and the difference between one. So this is just to have an expression that have the usual curve we see when we calculate fusion cross section. So it's nothing to do with Won's formula. Also, we can refine the problems we have in one formula if we use these renormalized fusion functions that we divide by this coefficient that is nothing but the coupled channel divided by one channel calculation. So in fact, what we are showing here is the difference between coupled channels and one channel calculations. So using this method, we studied the total fusion. I will talk about only heavy systems here because our method to calculate complete and incomplete fusion has also applied by now to the heavy systems. So that's why I will concentrate in my talk here only in heavy systems. I am showing here a result from some, although here we have only one light system because this method, as I said, we have a universal function and we can put here any system with any mass or charge or whatever. So to see the effect above the barrier, we use the linear scale. To use below the barrier, we use the logarithmical scale. Concerning the total fusion, we see that also we need a reliable potential in order to derive barrier parameter needed to reduce the experimental data and to obtain this X in the horizontal axis, in the axis, in the axis. So this is important too. People always sometimes say, "Oh, but you need the São Paulo potential." Okay, you don't need São Paulo potential. You need a bare potential if you want to use another potential, double folding potential obtaining from using matter densities from systematics or from experimental data. You can use it. The important is that you have a reliable potential and you use the same potential in order to compare or the system you have in mind. Otherwise, of course, if you use different potential to derive these barrier parameters, you will obtain different conclusions. What you cannot do at all is to use the fit to the experimental data to derive these barrier parameters because the experimental data already considers all the couplings. Not the couplings, is the reality. If you want to study the couplings, you have to have a barrier parameter to derive a bare potential to derive these barrier parameters. So the conclusion we arrive here is that above the barrier.
Sorry, Lubian, just to be clear here, what you're plotting here are just the data versus this fusion function, not the actual CDCC calculations, right? Am I right?
No, this is a Cooper channel calculation included. Thank you for the question because this is sometimes something we have done so many times and I'm not saying all the details. Thank you, Filomena. So this is a Cooper channel calculation included all the bound states of the projectile of the target, only that. So in this case, in the case of Wiggly bound nuclei, we include only the ground state and the excited state of the targets. No transfer. So
no continuum, no transfer.
No continuum, no transfer. So the effect we could see here is the entangled effect of the transfer and breakup, in fact, not only breakup, okay? So what we see is that above the barrier, there is no effect. If we use the systematic São Paulo potential, because when I perform CDCC calculation, I will show a slightly different result later. But by now, this is what we have published using the São Paulo potential with the systematic of the matter density that is in it. Because sometimes people say that this São Paulo potential was meant for the elastic scattering. That's not true. The São Paulo potential is the real part of the São Paulo potential only. Then it was introduced two systematics, one for the elastic scattering that is using the imaginary part that is 0.78, the real part, but this is for higher energies, at least no higher, but at least higher than not near the barrier, because it does not tend to accord the couplings. And if you put the couplings, you have to use a short range potential because otherwise you have double content. Also, there is another systematic using 0.6 in front of that, but I will not talk about this because it's not concerned to this calculation we are doing here. So concerning the complete fusion, we observed a hindrance of about 30% for these heavy targets above the barrier and some enhancement below the barrier. Against only performing Cooper channel calculation include, here is explicitly written, Filomena. We did not include any resonance even in the projectile. and only couple channel calculation included the inelastic excitations of the target. Okay. And
Yeah,
for
thank
the
you. Thank you.
okay, and for the halo nuclei, in this case is helium-6 or other neutron rich like helium-8 and beryllium-11. In this case, except the data for helium-6 plus gold, 97, there is a hindrance of the total fusion. In this case, remember that the experimenter does not separate the absorption of the core and on the complete projectile. So it's slightly different the situation here. So this is the main conclusion. I just want to remember that this is the situation we have when we study the effect of the breakup on the fusion cross-section. Again, not only breakup plus transfer. In fact, we now, at this moment, we are able to calculate a transfer quite well, but okay, at that time, we were analyzing a lot of systems. As you know, the transfer calculation are more time consuming, and we decided not to do all the complete calculation. Okay, we obtained the systematic for several systems. We have a complete fusion enhancement to barrier energy and suppression above the barrier when compared with that it should be without a dynamic effect. I emphasize that this is a dynamic effect of breakout and transfer channels. But how to measure and calculate this complete and incomplete fusion, this is the main subject I want to discuss with you right now. So finding the complete and incomplete fusion cross-section is a great challenge for both experimental theories. We know that we have only few experimental data. It's very improbable to have all this complete fusion and incomplete fusion for each fragment and the total fusion or whatever, because it's quite difficult to measure. And also there is a lacking of theories that can calculate all these in complete details. And also when you have a corpus plus neutrons or neutron, you cannot separate this from the experimental point of view, and most of the experiments determine only total fusion. There is an individual complete and incomplete fusion measure. Some examples are this one that I've shown here, that is the one that I will discuss. In this case, I will discuss only lithium-7 and will show some preliminary results we have for the lithium-6 too. We started by lithium-6 and 7 and beryllium because the statistics of the experiment with this projectile are higher and the experimental data are with lower error bars. And these are more strong constraint for any theory, because in some experiment, if you have a radioactive beam, then the error bars could be big, and then it's difficult to calculate too, but it's more easy to describe this data because you have big error bars. So,
hello.
Yes.
Could you say why you don't mention the case of deuteron projectiles?
Well, it's nothing special for that. Sorry for my omission. The deuteron case can be included also, but in deuteron case you cannot separate. The transfer channel would be very important too. Filomena can say some words if she wants about that. In the case we are studying here, except for the very low energies, we are supposing that the match reaction channel is the breakup one. Even we are using targets that have low collectivity, because we are at this moment, I will show you, we are not including the collectivity of the target too. So this is our future plans. But by now we are not including in the same calculation, the transfers, the inelastic excitation or the core excitation of the projectile. So we are trying to use the more simple cases as a starting point, although they are not simple at all. Okay?
Thank you.
And thank you for your question, because for sure, deuteron is the oldest questions for nuclear physics. And so in my talk, I will talk about projectile that breaks in two fragments. I will describe this with this potential. It's the sum of two potentials of interaction of the two fragments with the target. Of course, to determine the states of the projectile, we will need the potential between these two fragments. The difficulty here is that we have a continuum state. Even if we truncate this state with some maximum energy, as we do when we perform usual coupled channel calculations, we will have always infinite number of states. So in order to have some way out from this situation, what people usually do is to change this continuous state by a basic, and more specifically, in the case of the fresco code, that is the one we use for in our calculation, the binning method is the one that is most common used, but is because it is already implemented in the code. So here I am, this example in the right side is not very good because as we know, when we construct these bins, we have to take into account that they cannot superpose each other in order to guarantee the orthogonality between them. But we include the bound states and the continuous states at the same time. In the left side is the one example of the discretization we have used in the case of lithium-7 and how we have described the two resonances in the case of the octupole angular momentum between the two fragments of in the alpha and triton in this case. So when we divide this continuum in packets with different angular momentum between the two fragments, we reduced our problem to the standard coupled channel problem with a finite number of coupled equations. But nevertheless, as everybody knows, it's a complicated calculation, time consuming, and we also have to be very careful in order to guarantee that our results are completely convergent. So we have to check all the parameters we have to check the potential we have used, we have to check the potential that describe the position of the resonances, the root mean square radius of the matter density of this nucleus. We have to describe all the quantities possible available with the potential we are using, and we have to guarantee that our result does not depend on our choices. So what we do in this case is to project the wave function in angular momentum and to solve the coupled equation to get the S matrix and the wave functions. Having this, we can calculate the fusion cross-section. So there is always a way to calculate the indirectly. So having this, the S matrix from this coupled channel calculation, we can determine the reaction cross-section, and taking the reaction cross-section minus the cross-section of the direct reaction channels included in this calculation, we can have at least the upper bound of the fusion cross-section, because if we don't include all the channels, the relevant channels, this will be the upper bound for the fusion cross-section, not the fusion cross-section itself. So the direct calculation in this case is to take the expectation value for these two parameters, but how to do that in details is what the people have been trying during several years. The first model were introduced by Hagino and Dasgupta. They perform a classical calculation. They solve a classical equation of motion of the two fragments interacting with the targets, and they obtain quite good results, as shown here for the complete fusion and total fusion. Of course, they can only talk about the fusion cross-section above the barrier, because this is classical. They have no tunneling, and they cannot describe the below barrier regime. Then Felipe Canto, Raul Donangelo, and Daniel Malta, they introduce a semi-classical model. In this case, they introducing the tunneling through the barrier. They have proposed several improvements to this model, but and they have obtained quite reasonable good result too for this. But there is some problems also in these calculations, and there are other development too. I'm just giving some minor idea of this calculation. I put all the reference. If someone wants to know the details, please can read this reference. The first try, sorry. to do a quantum mechanical calculation were performed again by Hagino, Vittoridaso, and Lenzi in this work, and later with a more complete model space by Alexis Diaz-Torres and Ian Afonso. What they did was, instead of using these two interactions, the imaginary part of the potential, instead of using these two potentials, they introduced a diagonal into the potential of the interaction of the target and projectile, the center of mass. Then they determined the total fusion as a sum, and this potential is diagonal. They obtaining the fusion cross-section, the total fusion cross-section, by summing the expectation value through all the channels of this imaginary potential. And they consider, that the absorption from the bound states correspond to the complete fusion, and the absorption from the continuum states is the incomplete fusion. This idea will be used in our method that we describe a little bit later. And it's an important point I wanted to fix. This method works very well for systems that have projectile that breaks in two fragments that have very different masses. So this is an example, for instance, the beryllium-11 case. That was exactly the one we used by then. In this case, if you are in bound state, you absorb everything. If you are in the continuum, if you absorb you absorb the center of mass, you will over-absorb at least one of the fragments, so it works fine. But if you use, for instance, lithium-7, that is one of the case we are studying in this case, exactly this reaction, lithium-7 plus bismuth 209 was the first one we studied. In this case, the two fragments has about the same masses. So if they are in bound state, if you absorb the center of mass, you absorb both fragments, that's right. But when they are in the continuum, you can absorb the center of mass, but you can even not absorb neither of these fragments. So in this case, this method does not work at all. So there is another method recently developed by Jean Lay and Antonio Moro, a very good method. I think that Moro will talk about this the next week. In any case, if you have any questions, you have Jean Lay here to ask. They determine the complete fusion indirectly by calculating reaction cross-section from CDCC optical, for CDCC calculations. They determine the inelastic cross-section from standard coupled channel calculation, including only the bound channels, elastic breakup from CDCC calculation, and non-elastic breakup of each fragment for the expectation Y model of Ishimura, Oster, and Vincent. They obtain very good results for lithium-6 for bismuth 209 shown here. These are the experimental data and the complete fusion. This is a very nice model, but cannot evaluate independently the incomplete fusion as a sum or even for each fragment. But of course, it's a very good model, one of the best we have at present. There is other models found in the literature. For instance, the one of Hashimoto et al. They perform a CDCC calculation. As probably you know, to perform CDCC calculation, we perform a transformation from these R1 and R2 coordinates of each fragment to the center of mass of the projectile that is usually represented by R capital, and the internal coordinate of the projectile that is represented by small r. And after they solve this system of coupling equation, they perform back the transformation, and they calculate integrals of the absorption of each fragment to determine complete and incomplete fusion. In this case, they studied, as Professor Johnson said, the deuterium plus lithium-7, the incomplete fusion of proton and deuterium with very good result. The only problem here is that you have a parameter of what is the maximum radius to consider the absorption from complete fusion to determine until this radius you have complete fusion, and until this distance we have incomplete fusion. In this line, Boselli and Diaz-Torres used similar method using projection operators to describe the time evolution of wave packets. They used this to determine complete and incomplete fusion of lithium-6 because Bismuth system, some qualitative result they obtain. This method is promising, but so far it has not been used to determine quantitative cross-section, so because they are developing the method still. There is another method by Mumbai group of Kailasa Shrivastava that they perform CDCC calculation using different short-range imaginary potential to determine complete and incomplete fusion, total fusion, switching on and off different components, and they determine this. There is the minor point of this method is that there is not self-consistent, not all the cross-sections are determined in the same calculations. So now I will start to describe our method that is based, as I said, in Hagino, Vituri, Dawson, Lacy method. But in this case, we do not use this. We do not consider that the potential is diagonal. So we study the individual absorption of each fragment. The potential used in our CDCC calculation are internal potential. For this reason, we choose a target that should not have important inelastic excitation. Otherwise, we have to use a potential that reach to the surface. Because if we use imaginary potential that reach to the surface, in this case, this potential will not be good in order to determine the absorption from this potential the fusion cross section. So we use a good Sasson protection like this with these standard parameters. We also have shown in some recently somewhere that the determination of this parameter is completely irrelevant as soon as it is short range, so it is inside, guarantees that you have only absorption inside the barrier. So then we divide the space as Hagino and coworkers did in two parts, the continuum and the bound states. So the absorption from the bound states is what we correspond to the direct complete fusion. So we are only considering here the bound states, that is in the case of lithium-7 is the ground state and the first excited state. Pay attention that we have here absorption here from both alpha and alpha line, although it's not written here. In the case and the absorption from the continuum, we study independently the absorption from each potential. So if we perform a projection in the moment space, projection in the moment space, and we zoom only about between these continuous states, we can determine now that the cross section from this continuous space will be the sum of the probability of absorption of the two spaces. This we will call the total fusion. And PJ, these are our probability of absorption of each fragment. So if we want to study the incomplete fusion of the fragment 1, it would be the absorption of the fragment 1 multiplied by the non-absorption of the fragment 2. The absorption of the fragment 2 will be the absorption of this fragment and non-absorption of the other fragment. The incomplete fusion, the total incomplete fusion will be the sum of the incomplete fusion of each fragment. And the sequential complete fusion will be twice the probability of the probability of the absorption of the fragment 1 and the fragment 2. If we sum of this probability, we will obtain the total fusion, that is the sum of the complete fusion, that is the sum of the direct complete fusion and the sequential complete fusion, plus the incomplete fusion. So we have now all the ingredients, all the details, the formulas for these probabilities as expectation of matrix elements between transition of different continuums or bound states are given in this, not in this paper, sorry, in the other one that is published in Physical Review at the end of the last year. Sorry. So how long have I been taking right now? I will now pass to the results. We will apply this to lithium-7 plus bismuth. We perform a CDCC calculation running Fresco. In this, we export the intrinsic and radial wave function. It is very important to emphasize that in this case, in the usual CDCC calculation, we need only the convergency concerning some quantities that depend only on the behavior of the wave function at large distances. But we are now performing calculation inside the barrier. So we need that the radial wave function are convergent also inside the barrier too. And I can tell you that this is a hard task. Then we use these wave functions of the projectile to determine the probabilities, and using our code, we can calculate the complete and incomplete functions. Here are the results for the lithium-7 plus bismuth. We see a very good agreement with the complete fusion and incomplete fusion. In the case of, sorry. This is only complete fusion and total fusion. Total fusion above the barrier, we have not a very good agreement, but I will explain in the next transparency why this should happen. In the case of this lithium-7 plus bismuth, the decay chain of alpha absorption, helium-3 absorption passed through polonium to 210, so they could not be separated. And then in the case in polonium-209 that have a half-life of 102 years, so cannot be detected. So the author claimed that above 36 MeV, this is the lower bound only. So that's why if we compare our incomplete fusion with the data, we see that we have good agreement until this region, but above this, we have overestimation that should be expected. And this is why we overestimated also the total fusion in this case. Okay, but all other thing that we have checked in this case is that the wave function of the lithium-7, usually in CDCC calculation, we take the spectroscopic amplitudes are equal to 1. So that is 100% the wave function of this alpha cluster structure in lithium-7. But we have experimental data at low energy that show that there is other transfer channel, important channel, that there is other breakup channels that are triggered by this transfer. So we cannot say that the wave function of the lithium-7 is 100% this cluster structure. So we investigating, we have this as a free parameter. We investigated this value, changing this spectroscopic amplitude, and there is a Watanabe estimation that the structure of the cluster structure of lithium-7 should be about 70%. So we then changed this spectroscopic amplitude between 0.7 and 1. This is if you look to the in the logarithmic scale, you will see almost no effect, especially if you have experimental data that have 10%. But if you put in linear scale and you want to have a quantitative description of the experimental data, this spectroscopic information might be very important. Also, another important things I would like to show you is that if we use the standard matter densities, for instance, the systematic of the San Pablo potential that is represented here by VPT, projectile target, or this cluster structure, we have completely different barriers. You see, this is the case when we have a cluster structure, we have a lower barrier, bigger radius, about the same curvature, but a little bit more bigger in the case. The barrier is a little bit wider in the case of the cluster structure too. So which implication this can have in the cross sections? Of course, this will immediately increase the cross section in the whole energy interval. So when we, okay, I can jump this because maybe we don't have time. So here are the results, not only for the bismuth that is very good as I shown here. So if we use this potential the usual projectile target potential to compare the experimental data, we see what usually we and other people have said in the past, that the complete fusion is enhancement below the barrier and hinder below the barrier. But if you use the V00, that is the potential that is obtained by the folding in the ground state of the each fragment with the target projectile, you see that you have hindrance in a whole energy interval, and almost at the very low energy, they completely coincide. There is no effect below the barrier. So the effect of the breakup is hindered the fusion cross-section not only above the barrier, but also below the barrier. Oh, my mouse. Here are the results for gold and tin. We see that the complete fusion, this is logarithmic and linear scale. We have quite good. You have all the calculation in this calculation have been performed with the spectroscopic amplitude equal to 0.8. We see a very good description with the data. In the case of platinum 198, we have data for very low energies. And we see that here we have some disagreement of our results compared to the data. As we have seen in the previous slides, we have to have about a convergence of the complete fusion to the one channel calculation and energy below the barrier. But we see here we have something that was strange for us from the phase size. So then we compare this is the imaginary part of the optical potential when you perform expectation value from the ground state of the projectile in one channel calculation. So we see that in the case of the projectile target, we have, this is the radius of the barrier. So if we use this W00, that is this potential obtained from even if this individual potential are short range, the one obtained by the folding through the ground state of the projectile goes for distances longer than the barrier. We know that we have, if we are talking about fusion, we have to have fusion only inside the barrier, but not after the barrier. So in this case, we perform a calculation with the WPT. Remember that this corresponds to the real part. Is different now. I'm talking about the imaginary part. So if we perform calculation with V00, but W00, we obtain this dashed curve. But if we use W00 and the imaginary part, we use this potential that only absorbs flux inside the barrier, then we get the correct cross-section. Here, I am putting this magnitude in two cases, one for L equal 3, and the L is not important because this is similar for independent on L. The relevance is that we have here for energy below the barrier and above the barrier. Above the barrier, you see that this integral is concentrated inside the barrier, but below the barrier, as the imaginary potential LSD, we have the major part outside the barrier. So we are taking absorption for something that is not fusion at all. That's why we corrected this using this WPT for calculation of the complete fusion. This is also how the fusion or the absorption depends on L for two different energies. In this case, you see that above the barrier, they coincide. So this F is not relevant above the barrier, but below the barrier, they are very different. So we performing this correction, we get to the very good, completely very good results. Now I come back to the reduction I talked to you earlier. In this case, we are reducing the same data for all the system we have. You see that the very good quality data, all they coincide in the same line. This is the universal function we want to compare to. In one case, we are using the barrier parameters obtaining with the systematic of the Sao Paulo potential, in which there is not considered the cluster structure of the projectile. In the other case, this is considered. In this case, what is 0, consider the structure, the cluster structure. You see that the hindrance is more bigger than usually it is reported when one uses this potential target. So different results can be obtained depending on the potential we are using. But if we are using a CDCC calculation to determine our cross-section, we have to compare to the potential used in this case. So the hindrance is bigger. The hindrance due to dynamic effect is bigger than, in fact, was reported in the past. Here are our result for incomplete fusion for all the systems involving lithium settings and lithium-7 and gold, tin, and tin. We see that in the case of the Triton, they are all represented in green. We have quite good agreement. But in the case of alpha capture, we have an systematic overestimation. So this is something we by now do not understand completely, and we are trying to understand if it is a problem of a potential we are using or problem of the data. All these data are obtained with the same technique, gamma detection. The data detected for the Australian group was using another method. So we are not saying, of course, we cannot say that the data are wrong, but if our methodology was wrong, we were not able to describe the Triton at all also. So we have some idea what could be the reason for what, but as we have not the final answer to this, I prefer not to say nothing. If someone wants to know our idea, I can say, but I prefer not to say right now. Some preliminary result for lithium-7. In this case, the cluster structure as the binding energy of the lithium-6 is lower. It is expected that the cluster structure of lithium-6 might be more relevant, so we use 0.9. These results are not published. So these are the results for the complete fusion in the upper figures for the in logarithmic and linear scales. If we use 0.9, we see that the agreement is quite good. These are the incomplete fusion, but there is no data in this case, so nothing to say. In the case of tin 124, again, the complete fusion is quite well described. The incomplete fusion of Triton is well described. Again, the incomplete fusion of alpha is overestimated. So there is something that we have to discover what is the reason of that. So the conclusion is that we have proposed a new quantum mechanical method to evaluate complete fusion and incomplete fusion in collision of weakly bound nuclei. The method was applied to lithium-7 plus heavy targets. Sorry if there is an missing S there. Heavy target systems. And the results were compared with the data. Considering that our calculation use standard interaction have no free parameters, the agreement between theory and experiment is quite good. Calculation for other systems are in progress, including medium mass nuclei, other projectiles. We are planning to do to perform calculation on lithium-6 on heavy targets, lithium-6 and 7 medium mass targets, include spectroscopic factors to try to find some way to determine this from microscopic calculations, include target excitations, as Moro have done with his own code. In our case, we are trying to write a new code, and also we are putting things inside Fresco. Maybe we have to talk with Ian Thompson about that. We are planning to include core excitations. We want to extend our calculation to four-body CDCC calculations, to perform calculation, for instance, for beryllium-8 collisions, include transfer channels. I put many question marks here because it is not obvious how to introduce different spectroscopic amplitudes for the wave functions, because different percent of wave functions are needed. The potentials, which one will be for different components, it is the same one, if it is the cluster is valid for transfer or not, because the particle is taken from one of the fragment or from the whole projectile. So a lot of questions here. Include breakup triggered by transfer. So most of these ideas requires another version of the CDCC code. And of course, this is a long plane, very ambitious plan. This is our team members. First of all, Felipe Canto, that is a more senior member of our team, and then our postdocs, Yanni, Jonas, and Mariani. Thank you very much for your attention. Sorry because I took 10 minutes more than you gave to me.